So we will continue determining Fibonacci numbers, except this time we're going to be using the golden ratio. It says use the relationship of the golden ratio to determine the 15th and the 16th Fibonacci numbers. Now keep in mind that the golden ratio is a ratio. It's like a fraction. So if we have a ratio, let's just say A over B, in order for this to be a golden ratio, it has to equal to the sum of these two values, A plus B, divided by the numerator here of A. And if these are equal to each other, then these are golden ratios. So for example, if we make A equal to the 12th Fibonacci number, and if you recall, the 12th Fibonacci number equals 144. And if we make B equal the 11th Fibonacci number, and if you remember, the 11th Fibonacci number is 89. So if we have A over B, if we take 144 over 89, then that's got to be, and this is A and this is B, then that's got to be A plus B, which is 144 plus 89. That gives us the 13th Fibonacci number, which is 233 over 144. A over B, A plus B over A. So to determine if these two ratios are equal to each other or proportional to each other, we simply cross multiply. So we'll take 144 times 144. That's 144 squared. Is that equal to 89 times 233? 144 squared, that's 20,736. And is that equal to 89 times 233? That's 20,737. Whoa, very close. Not quite, but very close. They're approximately the same. But as these Fibonacci numbers get larger, as we go further and further down the sequence of numbers, these numbers get bigger and bigger and bigger, and the significance between the last digit becomes smaller and smaller. So if we actually determine what is 144 divided by 89, 144 divided by 89, well, if we approximate that to 4 decimal places, it comes out to be 1.618. It's right around there approximately. And if we do the same for 233, divide that by 144, that's also approximately, and if we do it to 4 decimal places, 1.618. So they're approximately the same. There's more digits after it, but if we go ahead and we round it to here, they're approximately the same. And again, as these Fibonacci numbers get bigger and bigger and bigger, as we go further down the sequence, this value starts to level off. And what does it level off to? Well, it levels off to 1.618034. We will use 6 decimal places to express it. And since this is an irrational number, in other words, it doesn't terminate, it's dot, 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 it continues on, we label it as phi. That's how I write phi. That's the best I can do it. And phi is a Greek letter, lowercase Greek letter. So phi is equal to 1.618034. So if we look at this, that means if I take some Fibonacci number and I divide it by the Fibonacci number before it, and as the Fibonacci numbers get bigger and bigger and bigger, it starts to come to phi. It starts to get closer and closer to phi. And what's phi? Well, we approximate it to 1.618034. So rather than having to add successive Fibonacci numbers to determine the next Fibonacci numbers, we can use phi to do that. So for the 15th Fibonacci number here, we know that the 15th Fibonacci number from the previous example is 610. So if the 14th Fibonacci number is equal to 377, then all I have to do is add the 13th Fibonacci number, which is 233, add that to the 377, and it's going to give us the 15th Fibonacci number, which is 610. But we don't have to do that. We could simply just go ahead and take the 14th Fibonacci number, which is 377, and multiply it by phi. And if we go ahead and we do that, it comes out to be approximately 609.9988. You won't get it exactly because this is an irrational number, but it comes out to be 610 if we go ahead and we round it. We do the same for the 16th Fibonacci number. The 16th Fibonacci number will be the 15th Fibonacci number, which is 610. And rather than take 610 and add 377, we go ahead and we multiply it by phi. And it comes out to be approximately 987.0007, or in other words, 987. We just go ahead and round it to 987. And of course, 377 plus 610 is 987. So here we're using phi rather than have to add successive Fibonacci numbers. And there we go.